Um, okay, hi, my name is Selma, and I'll be presenting the ECE561 project, which is a research project called Artemis Mixed Analog Stochastic in DRAM Accelerator for Transformer Neural Networks. And this project was done under the supervision of Professor Siddhi Pasricha and uh, in collaboration with Professor Ishan Thakkar from the University of Kentucky. Okay, so first of all, just a very brief motivation behind this project. So why in-DRAM computing for transforming neural networks? First of all, in general, why in memory computing? We covered this a bit in the in this course, which is the memory wall bottleneck. Since now we are seeing that the compute capabilities are significantly limited by the cost to communicate energy to and from off-chip memory. In fact, like the energy for data transfers between processors and off-chip memory exceeds that of a floating point now operation by a factor of 2 orders of magnitude, which is very significant. In terms of DRAM, it's very widely already used. It's already integrated and found in pretty much all of our computing platforms. It's easily integrated. It provides relatively low energy and read-write latencies. One drawback is in some cases, like integrating the compute circuits within the DRAM chip is not exactly like straightforward. However, like there are other memory technologies that can be used, but these usually have a lot of issues and limitations such as reliability issues. In terms of transformers now are pretty much established as the model of choice for all your natural language processing problems, and is even already being used in vision tasks and used in many prominent applications. And the thing about transformers is that they can be huge. Like they can have like billions of parameters and even more. So this is why like in DRAM computing, it's a very there's a lot of work that's looking at in-memory and in DRAM computing for transforming neural networks. So just very briefly, like a bit of background, this project is based on the conventional DRAM structure, which follows basically a hierarchical structure. So we have the chip, which is shown here, composed of several banks. Each bank is composed of several subarrays, and each subarray is composed of several tiles. So how we would perform the operations within each tile, if we focus on one column within a DRAM tile, we leverage this work here, which is called RC. So what they proposed is just putting one diode between each pair of bit cells, as shown here. And then if we want to perform an AND operation, for example, all we need to do is first copy the value of X into C. We can just do a copy operation by simultaneously activating both word lines. Next, we would copy Y into C. And then finally, like, since we have this diode here, what will automatically happen is the charge in D will escape to C. So now as we can see, the D holds the output of X ANDed with Y. If we want to perform an OR operation, a very similar method is used, just a different sequence of events. However, like this is to perform only one AND operation. If we think of more complex operations such as multiplications and addition, it can take a lot of cycles if we break down these operations into digital operation, namely AND and OR operations. In fact, like one of the previous works, called DRISA, to perform one MAC operation requires up to 222 MOCs, and then MOC is a memory operation cycle. And this is why for this project, we focused on stochastic or unary computing. What that entails is each number is represented by the probability of the occurrence of ones in the bit stream. So for example, if we want to represent 6 by 10, we would have a bit stream of 10 bits, and we would have like 6 ones in them. So technically for each n bit, we need 2 to the power n bits to represent it, to be represented stochastically. However, despite like this significant storage overhead, the benefits it presents is that complex operations can be done using simple logic gates. So if you want to multiply these two numbers, for example, all we need to do is use just a simple AND gate. Similarly, an addition operation can be done using just an OR gate. So this brings us to the main project, which is Artemis. So what it achieved overall is uh, presenting a novel in DRAM hardware accelerator called Artemis, which combines stochastic and analog computing principles to perform transformer inference acceleration. We devised a novel in DRAM analog accumulation unit using customized metal oxide metal capacitor. And we efficiently combined data flow and control mechanism and created a data movement microarchitecture to move the data between the different banks and the different subarrays in a way that reduces energy and data movement latencies in DRAM. And finally, we performed comprehensive comparison with several state-of-the-art in DRAM transformer accelerators. So this is an overview of the Artemis architecture. We first have like within each DRAM tile, this is where we perform on Mac operations. So here, like using the bit line logic, we perform multiplication stochastically using mainly ROC, which I explained in previous slides. And then to perform the accumulations, we use the MOM capacitor, metal oxide metal capacitor. And the thing about MOM capacitors is that it's basically put in a 3D manner. And like using a capacitor for accumulation, we want it to be as large as possible since larger capacitor area translates into larger capacitance, which translates to more numbers that can be accumulated or more charge that can be accumulated in a single capacitor. So this way we can have a capacitor as large as our tile area without actually increasing the overall area of our architecture. And then since we're doing like multiplications and stochastically, and then we're doing accumulations in the analog domain, and then some operations need to be done in the digital domain, we have designed like small and efficient circuits, very low overhead to handle these data conversions. And then finally, we have near subarray compute units that are associated with each subarray to perform the different other operations that are needed, such as nonlinear activation functions and reduction. Next, just briefly talking about how we do the Mac operations. So first of all, like I said, we do the multiply operations stochastically. So we do this using the TCU-based deterministic multiplication method. TCU just translates to transition coded unary. It's a different way to represent unary numbers. So as we see here, all the ones are grouped together at either end of the stochastic number. And how we use that is to perform the multiplication, we just need to pass the first operand through a binary to TCU decoder, which we have in our near subarray compute units. And then the second operand also is passed through a binary TCU decoder. However, it is followed by a bit position correlation encoder. And then the output of these two numbers, we just add them together, and this is how we do the multiplication. So the ANDing, like I said, we completely do it within the bitline logic of the DRAM tiles. So this is all handled with just ROC, like bitline, the method of how we do the AND operation, and we don't actually need like these AND gates. Next, as I said, when we do the accumulations, we want to be able to accommodate like the largest number of accumulations possible before we have to do the data convergence. So we performed detailed simulations to determine like these are the colors here represent different capacitance values, and each step in the figure represent one accumulation. So we did this analysis for several different capacitance values, and we determined like the maximum number of explanations that can be accommodated with each. Um, and the linearity dictates that the accumulation is being done correctly. So, and then finally for the data movement, it is the major bottleneck with in DRAM computing, same way with like regular processors. So we also devised like a very in detail how the data communication will happen, and we are following a token-based data flow as opposed to a layer-based data flow. So for the experimental setup, we compared against four state-of-the-art in DRAM transformer accelerators, which are Transpim, HIMA, Rebirth, and um, our accelerator. And then all the architectures are evaluated using 22 nanometer DRAM technology. I developed simulator in Python to be able to estimate the area, performance, and energy cost associated with our accelerator. The energy estimates were all obtained using cacti, while latency values were computed using detailed LT-SPICE simulations. And we used an 8 gigabit DRAM substrate. And these are the results. So Artemis was actually able to surpass all other accelerators and compute platforms. We achieved on average at least 3 times in speed up and at least 1.8 times lower energy than all the other platforms that we compared against. There are still, however, some open challenges. As I said, data communication, like although we devised like a detailed data communication model, it's still like we are doing the computations and multiplication, the other accumulations like very fast using the methods I explained. However, we're still limited by the time that it takes to move the data using the shared bus between banks. So this is still like an open challenge, and some of the possible solutions is maybe we can connect the subarrays using access transistors. This will, however, present like a bit of a challenge, but it is one way that we can explore, as opposed to just using shared data bus. And another solution can be using, for example, optical links within the DRAM substrate for fast and efficient data transmission, or maybe just use optical links between the different layers of the high bandwidth memory, like the chips stacked together. And this is all. This is my project. Thank you so much for your time.